Although we will be spending the great majority of our time and attention going forward in mathematics dealing with variables and relationships between variables, it is still valuable to go back to the very beginning and consider the most fundamental basis of mathematics, the number. A number is, basically, a concept that we use to assign and compare a value. If we have more of something, we can say that we have a greater number of that something, or that the numeric measurement of it is greater. This abstract idea has its basis in our most tactile and physical reality, and was one of the essential concepts that gave support to cultural and scientific and economic development in early human societies. The ability to count, to assign a number to a certain amount, and to state whether something is greater than or lesser than another amount by again another certain amount, remains one of the most necessary parts of human consciousness. As that consciousness and those societies developed, so did the complexity of that number system. Basic counting of units eventually required divisions of an individual unit. Certain measurements and calculations resulted in numbers that didn't fit the previous patterns, and so on. We can arrange these layers of complexity into a system of sets or groups, where a more basic set is a subset of a more evolved set. Start with the counting our natural numbers, 1, 2, 3, 4, 5, and onward. This set is traditionally labeled n. Include 0 in the set of natural numbers, and we get the whole numbers. The set of whole numbers is commonly called W. Include negative numbers with whole numbers, and we have the set of integers. Integers are labeled Z after the German word Zahlen, or to count. If we only have part of a whole, we can express how much we have in terms of how many parts are required to make a whole and how many parts we have on hand. This comparison of integers creates the rational numbers, which we more readily identify as fractions. The set of rational numbers is Q after quotient. In certain cases, we find numbers that cannot be expressed as fractions. These are the irrational numbers. That set is labeled I. If you combine the rational and irrational numbers, you have the complete set of real numbers R. Any real number can be compared to any other real number, and we can definitively say that one is greater or lesser or equal to each other. We can even express this relationship visually using a number line. Oh God, a number line, you say. Number lines are for little kids. What's up with that? We use number lines in like 4th grade. Sure, and it made perfect sense then, and it makes perfect sense now. Number lines are profoundly underappreciated organizational tools. We'll actually be doing extensive work with an evolution of the number line mentality throughout this course. Numbers by themselves are the absolute foundation of math, but the self-generating relationships between those numbers, the properties of real numbers, are what gives us the framework for operations and other conceptual developments. For operations with numbers to hold together as a system, a series of properties must be maintained throughout these operations without exception. A basic list of these properties includes closure. Two real numbers added or multiplied together must result in a real number. The commutative property. The associative or grouping property. The distributive property. Identities, and inverses. We can also consider multiplication by zeros something of a property, even as it's also an illustration of the definition of multiplication. 7 times 0, or 7 zeros, is still 0, for example. Let's take a step back and look at inverses, specifically additive inverses. Additive inverses are interesting because they establish the presence of negatives. What number added to a certain natural number equals the additive identity 0? But if that certain number at the start is already a negative number, then the inverse is the negative of that, which is a negative of a negative, or it must be a positive. If a negative number plus a positive number equals 0, and a negative number plus the additive inverse, or negative of that number, equals 0, then the negative of a negative must be positive. We won't be doing much with proofs this semester, but we have effectively just proven an important consideration of inverses. So those two numbers are the same, or they have the same value. And from the very beginning, we've considered values and comparisons of values, whether some value is greater or less than another. From here, we get the trichotomy property. Given two numbers a and b, exactly one of the following is true. A is less than b, a is equal to b, or a is greater than b. A cannot be both greater and less than B or equal to it at the same time, in other words. Equality, of course, takes a certain priority in our considerations. We like it when things are equal to each other, and the process by which something is shown to be equal to something else is profoundly important. Given that two numbers are equal to each other, four different properties are then made apparent: the reflexive property, the symmetric property, the transitive property, which is the one that we used earlier for that proof, and, by extension, substitution. A sort of equality even shows up in cases where the values themselves are definitely not equal. For example, consider any number and its negative, say 5 and negative 5. Even though they clearly don't have the same value, they are exactly the same distance away from 0. Distance is always a positive value, which we can also call the absolute value. The absolute value of both 5 and negative 5 is 5. For any number, the absolute value of that number is either the number itself, if the number is positive, or the opposite of that number if the number is negative. In either case, it identifies and measures the distance to 0. Quick little note about working with absolute values. If the absolute value of a variable is equal to a number, you must account for both the subsequent values of that variable. Although we tend to focus on equalities in equations, as we said we have this preference for it earlier, inequalities are also profoundly important for mathematical figuring, and also tend to show up in everyday life in situations with terms like at least, no more than, or between this and that. Because an inequality does not specify an exact value, we talk about an interval, a range which contains all values which fulfill a certain arrangement. Sometimes these intervals are open-ended, sometimes they're bounded on both sides. Sometimes they contain a particular starting point, sometimes they specifically exclude that starting point. Interval notation on a number line can take two forms. One is the open circle filled circle, one is bracket parentheses. Quite honestly, pick a favorite and stick with it. They're both valid, but consistency is appreciated. To solve an inequality problem, we perform operations in much the same way as we would solve an equation, but with the intention of finding that interval which satisfies the conditions. Checking your work is a healthy habit with all mathematical calculations, but especially so with inequalities. That proof by trial will become an important part of many of our efforts in the near future.